All right, so let's put the math to work and see how these numbers work out. Okay, so let's consider a scenario where we have a voltage with a peak of 100 volts. So let's draw the sine wave. And we have a V peak equals 100 volts. Okay, right there. So now the question is, we've got some different angles here to ask what is the instantaneous voltage at these angles. So the first one is 65 degrees. So if V peak happens at 90 degrees, what is the instantaneous voltage here at 65 degrees? Well, to answer that question, we have to draw a right angle triangle. So remember, the hypotenuse of a right angle triangle is the rotating vector and the magnitude of this rotating vector is always the same. So we can see here at 90 degrees that the magnitude of the rotating vector is equal to V peak. So when we draw our right angle triangle, V peak, 100 volts, is the magnitude of the hypotenuse. That is the magnitude of the vector. But when the vector is at 65 degrees, what is the distance from the peak of that vector back to our reference at 0 degrees? There's our right angle triangle. And so what is that height right there? So this is the opposite. This is the hypotenuse. We have an angle. So we're using the sine function. So the sine of the angle theta is equal to the opposite over the hypotenuse, means that the opposite is equal to the sine of the angle theta times the hypotenuse. So there's our equation that we're going to use repeatedly to calculate the instantaneous values at different angles. So the first one asks the opposite, which is the instantaneous voltage, is equal to the sine at 65 degrees times 100 volts equals 90.63 volts. That's the instantaneous voltage at 65 degrees with a waveform that has a peak of 100 volts, 90.63. Okay, really fairly straightforward when the angle is less than 90 degrees, because a right angle triangle, we know that the angle is somewhere between 0 and 90. Gets a little weird once our angles start to build beyond that. So let's figure out how this is going to work for us. So the question now is, what is the instantaneous voltage at 142 degrees? So where's 142 degrees? I don't know. It's somewhere over here. So there's the instantaneous voltage we're trying to calculate right there. Well, for starters, you can just let the math do the work. Okay? Draw a right angle triangle because we know that's the solution. There's our right angle. Our hypotenuse is our V peak, 100 volts. We're looking for the value of the opposite. And the angle is 142 degrees. So we just write it in there, 142 degrees. Okay? So the opposite, which is instantaneous voltage, is equal to the sine of 142 degrees times 100 volts. So we just take the numbers and we plunk them into the equation and we get an answer. And our calculator spits out a number, 61.57 volts. And we're done. Move on. But hang on. Does that bother anybody? 142 degrees as the inside angle in a right angle triangle? That doesn't exist. So what's happening here? What's going on? Well, let's go back to here. Let me draw another one. Well, actually, let's just clean this one up. So maybe that vector's in about the right spot. right there is our 142 degree angle. Okay, what we can do, because we're asking about the height, right? So just take the end of this vector and bring that back down to our horizontal plane. And there's the inside angle of our triangle. And what is that angle? Well, it's the full 180 minus the 140. So 180 degrees minus 142 degrees is equal to 38 degrees. So our triangle now looks like this. Still a right angle triangle with an angle of 38 degrees. Well, let's try this again. The opposite equals the sine of 38 degrees times 100 volts equals, and it's the very same number, 61.57 volts. Okay, so you can just blindly plunk in the numbers and let the math do the work. Or you can say, hang on a minute, I need an actual right angle triangle, and I need an angle which is something that makes sense, not this 142 degrees as an inside angle. I need a real angle that makes sense. No problem. Same answer. Okay? It's all good, right? Not quite so fast. Let's move on to the third example. And now, I guess I could have left that there. That's okay. Now we're asked, what is the instantaneous voltage at 350 degrees? So that is very nearly the end of our cycle. It's way out here. Okay, way out there. So let's draw the triangle. Oops. That's the right angle. This is 100 volts. This is what we're trying to solve for. And the angle is 350 degrees. Okay, really starting to hurt the head. Okay, to think that the inside angle of a right angle triangle could be 350 degrees. Doesn't make any sense. But let's let the calculator deal with it. So the opposite equals the sine of the angle 350 degrees times 100 volts. And we get an instantaneous voltage of negative 17.36 volts. Why did we get a negative answer? Because we're down here, right? That is negative 17.36 volts. Okay, it's all good. Let's go through the effort of making a real triangle, though. Okay, so once again, we're back to our grid. Okay, where is our vector? It's at 350 degrees, which is there. And here's our right angle, and here's our angle right here. And what is that angle? It's the full 360 minus the 350 gives us 10 degrees. So let's do the math. Opposite equals the sine of 10 degrees times 100 volts, which is our peak voltage, equals 17.36 volts. So here's the thing that I want to highlight. We are not done. Okay, and this is going to become a recurring theme. Your calculator gives you an answer. Okay, but it's not the end of the problem solving, which is weird for us. We're accustomed to plunking numbers into the calculator. It gives us an answer, and that's the answer, and we're done. Okay, we are not done. 17.36 volts is not the right answer. Negative 17.36 volts is the right answer. Okay, there's a couple of ways. Well, the first thing is to just do the work like this and say, okay, well, I've got the number. Now I know the number, but I realize that it has to be a negative value because we're down here in the sine wave below the 0 volts line. Okay, the other thing that you might do is to recognize that this 10 degrees, okay, remember, positive rotation is in this direction, and our vector is 10 degrees in the reverse direction. So if you were to place a negative sign right there, your calculator would give you a negative sign right there. So we have reached a point in our math where we've got lots of choices. There are different ways to go about solving the problem and getting the right answer. Okay? For some people, that's an exciting prospect. For some people, that's a terrifying prospect. Okay? But the reality is that once we move beyond the simple 0 to 90 degrees and we start getting into nonsensical angles, inside angles, or triangles, okay, we can deal with that in a variety of ways. Okay? Which is why the exercise sheets become so important, because it forces you to do this sort of work a number of different times and from a number of different angles. Okay? Because this math is all about solving for the instantaneous voltage. Okay? But the exercise sheets are going to ask you to come about this in the other direction as well. I'm going to tell you the instantaneous voltage. The question is, at what angle do you find that? And that's where this conversation about the calculator not giving you the final answer really comes into play. Because any given instantaneous voltage exists twice on our waveform. Okay? 50 volts and rising, 50 volts and falling. And here's some terminology for you. Right here, this is negative 50 volts and rising, because it is rising in magnitude towards the negative peak. Okay, so it's rising in magnitude. And then 50 volts over here, negative 50 volts and falling, means that it's falling back towards 0 volts. Okay, falling away from its peak, falling back towards 0. Okay, so this is actually a rising value, and this is actually a falling value, because it's an issue of the magnitude away from the 0 volts. Okay, so that's the one other detail that's going to be necessary for you to be comfortable with as you get into the exercise sheets.